Welcome to Maths with EJD. In this video, I'll be talking about countable and uncountable sets. So let's start with countable sets. Countable sets. So a set is called countable. A set is called countable or countably infinite. Countably infinite if its elements if its elements can be put in one to one correspondence with the natural numbers. Of course, the natural numbers are, we have this fancy symbol for it, and that is normal counting numbers 1, 2, 3, and so on and so forth. So if you can actually list a set to correspond with the natural numbers, then you can say that that set is countable or it is countably infinite. So this means that you can list the elements. You can list the elements of the set. You can list the elements of the set in a sequence. You can list the elements of the set in a sequence, even if the list is infinite. Even if the list is infinite, okay? As far as they can actually list one after the other. Okay, so you should also know that a set is countable. A set is countable if it is either finite, or countably infinite, What that means is that, of course, we already came across the idea of finite and infinite sets. For a finite set, you can list all the elements. But for an infinite set, you cannot list all the elements. But when you come to the idea of countable and uncountable sets, it's basically the fact that, so if it is finite, every finite set is countable. In the same way, every infinite set whose elements can be listed is also said to be countable. And that is where the idea of countably infinity comes in, right? So that's that. A set is countable if it is either um if it is either finite or countably infinite. Okay, if you can list all the elements, or if you cannot list all the elements, but even if you cannot list all the elements, but at least you can write it. You can list the elements out one after the other. So let's go for examples. So the set of natural numbers, of course, the set of natural numbers, that is, because that's even the standard, like anything that can correspond with it. So definitely natural numbers will correspond with itself. So the set of natural numbers 1, 2, 3, 4 is countable. So this is countable. And what is the reason? Because you can map each element to itself. You can map each element to itself. That is something like, you can say n is mapped to n, meaning we can 1 to 1, 2 to 2, and so on and so forth. Because every other thing that can be matched with the natural number, list of natural numbers, is actually said to be countable. Okay, let me take another one. The set of integers. So this is the set of natural numbers. This is the set of natural numbers. And we said it's countable. So let's go for the set of integers now. The set of integers. The set of integers. And it has this fanciful symbol, which is z with this thing in between. So the set of integers are simply whole numbers, whether negative or positive. So if you're coming from -5, so I mean from negative infinity to say -5, -3, okay, -5, -4, -3, -2, -1. 0 is also an integer. 1, 2, 3, 4, 5, and so on to positive infinity. So that is the set of integers. So this also can be said to be countable. It is countable, though you cannot list all the elements, but at least you can list the elements one after the other. So it is also said to be countable, although it includes negative numbers. You can list them by alternating between positive and negative integers like 0, 1, -1, 2, and so on and so forth. So, you can rewrite this actually like this. So you have 0, 1, -1, 2, -2, 3, -3, and so on and so forth. So actually you can list it as a set of and as something that corresponds with the natural numbers. Really important. Okay, so we go for the set of rational numbers. The set of rational numbers. So from the word rational, right, you see rational numbers, if you like. So the set of natural rational numbers, which is represented using this Q like this. So it's actually so the set of rational numbers, right? It's actually the collection of all numbers P over Q, such that P and Q are both elements of integers. They are both integers. These are rational numbers. Okay, but the question is, are these actually countable? Okay, so are they actually countable? Of course. So as far as all the integers go, right, you can start from 0 and you have 1/1, 1/2, 1/3, 1/4, and so on and so forth. So we also say these ones are countable. They are countable. Although it might seem there are more fractions than integers, they can be listed in a way that matches each rational number to a unique natural number. So you can say that the set of rational numbers are also countable. They are also countable. Okay. So with that we talk about we bring to an end the discussion about countable sets for now. So let's move on to uncountable sets. Uncountable sets. Okay. A set is called uncountable. A set is called uncountable if it is not countable. Of course, you already know what it means for a set to be countable. A set is countable if you can list its elements to correspond with the natural numbers. So a set is uncountable if it is not countable. That is, there is no way to list, there's no way to list all its elements in a sequence that matches them 1 to 1 with the natural numbers, Okay. It is worthy of note that uncountable sets have a greater cardinality, which is size. Of course, we know cardinality is the number of elements. Uncountable sets have a greater cardinality than countable sets. I mean, for obvious reasons, right? Something that can be counted is finite. You can pinpoint them, but something that is uncountable keeps going on and on. Okay. So let's take some examples again. Examples. So first, let's talk about the set of real numbers. The set of real numbers. Set of real numbers. Okay. The set of real numbers, and that is represented using this fanciful R. Okay. The real numbers are uncountable. They are uncountable. In fact, to even list real numbers is a difficult task. You just know that the real numbers are numbers that are not imaginary. And it involves decimals, fractions, everything you can think about that is not complex. Complex is the idea of square root I, which is square root of -1, So anything that does not involve this is real. So decimal, fraction, everything is real. So to even list it out is a big problem. So they are uncountable, right? This can be demonstrated using Cantor's diagonalization argument. So there's something called the Cantor's diagonalization argument. Diagonalization argument can demonstrate its uncountability. So what does Cantor's diagonalization argument say? It simply says that no matter how you try to list, no matter how you try to list the real numbers, you will still be missing something. No matter how you try to list the real numbers, some real number will always be left out, no matter how hard you try. Some real number will always be left out for obvious reasons, right? So, real numbers include 0, 0.001, 0.000001. I mean, if you increase the zeros to like 1 million, it's still real. So no matter how hard you try, you cannot list all possible real numbers, no matter how you try to list the real numbers, some real number will always be left out. That's the Cantor's diagonalization argument. Okay, so let's take another example, and that is the set of real numbers between 0 and 1. Interesting. So the set of real number is such a large thing already, but then if you even narrow it down to 0 and 1, it's still a problem. So the set of real numbers between 0 and 1, between 0 and 1. Okay, that's like 0, 1. Every real number here. Even this interval of real numbers is uncountable. So this is still uncountable. Just like the demonstration I did the other time. So if you have 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.9, all of that, they are all real numbers. So if you even go down 0.0001, so no matter how hard you try, you cannot list all these elements. So this is still uncountable. Even this short interval, the real numbers within any interval, no matter how small, cannot be listed in a way that matches them one-to-one with the natural number. So this is still uncountable. So let's talk about the concept of cardinality. Of course, I've talked about it previously, but let's talk about it now in the context of countable and uncountable sets. So, concept of cardinality. Okay, so cardinality refers, right? Cardinality refers to the size of a set, the size of a set, or simply the number of elements, the size of a set, which can be thought, which can be thought of as the number of elements, as the number of elements in the set, as number of elements in the set. Okay, again, for finite sets, the cardinality is simply the number of elements. It's simply the number of elements. That's for a finite set. However, for infinite sets, cardinality helps compare the sizes of different infinite sets. Though you cannot list all the elements, but cardinality can still help us to compare the sizes of different infinite sets. Okay. Now, if you talk about, so we have some groupings, right? You can talk about finite sets, for instance, finite sets. So the cardinality of a finite set is just the number, of elements. It's just the number of elements in the set. For example, the cardinality of the set A, B, C is simply 3, because that's 3 elements and that's all. So that's for finite sets. What if we talk about countable infinite sets? We already talked about countability and uncountability. Countable infinite sets. So the sets are infinite, right? But they are still countable. That means that we can list them in such a way that we can match them with natural numbers. So how do we talk about the cardinality of countable finite sets? So the cardinality of any countable infinite because you cannot list all the elements, countable because you can list the elements in such a way that they match with the natural numbers. So that's why they are countable infinite. So the cardinality of any countable infinite set is denoted by some special kind of, and I hope I can write it well. So it's something like this. It's some special n like that with a 0, and it's the aleph null, or what you can call the aleph 0. So I'm sure I didn't write that well. So it's some special n 0 like that. So the aleph null or aleph 0. So the set of natural numbers, integers, and rational numbers all have cardinality. All have cardinality. That's special n. Cardinality. Pardon me, I'm not writing that well. Cardinality n0. The aleph not, right? So all countable infinite sets have this cardinality aleph null. Okay, so now that takes us to the uncountable infinite sets. How do you talk about their own cardinality? Uncountable finite sets. Uncountable, rather, infinite, not finite. Uncountable infinite sets. Uncountable infinite sets. So the cardinality of the real numbers, the cardinality of the real numbers is larger, of course, as we know, is larger than aleph null. You know, that's the cardinality of countable infinite set. So it's larger than aleph null. So the cardinality of the continuum that's talking about the real numbers. The real numbers is often denoted by a special kind of C. You know, so a C that looks something like this, by a special kind of C, which stands for continuum, right? For continuum. And that C, that special C, I'm sure I'm not writing it well. So that special C is strictly greater than aleph null. Okay, so because of course we're talking about uncountable infinite sets. Okay, so let's talk about countability of specific sets. Okay, I mean that may just amount to some kind of repetition, but it's okay. So countability of specific sets. So one, let's talk about natural numbers. Natural numbers. So we have this natural numbers. So of course, we know it's countable. It's countable because you can list the set of natural numbers as 1, 2, 3, and so on and so forth. Okay. However, the cardinality, right? The cardinality is aleph null. Some special ends the n not like that. So the cardinality is aleph null. So of course, this is different from the sign for natural numbers. So the cardinality is aleph null. Okay. So 2, let's talk about integers. Integers with a special symbol. Integers. So again, this is countable. You can list the set of integers as, of course, 0, 1, -1, 2, -2, 3, -3, 4, -4, 5, -5, and so on and so forth. So you can make it correspond with the natural numbers. So as a result of that, the cardinality, because it is a countable infinite set, so the cardinality is still is that aleph null. Something like that. Okay, so let's talk about rational numbers. Rational numbers. That's 3 rational numbers. For rational numbers, which is this special Q, something like that. So rational numbers now. Again, rational numbers are countable. They are countable despite Q being dense in R. Countable despite Q being dense in R. So they are still a lot, right? They are still a lot, but then they are still, you can still pinpoint them. You can still pinpoint them. So you can list all rational numbers by arranging them in a sequence. Okay, can arrange them in a sequence. A very good example will be starting from 0. So you can have 0, you can have 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, 1/9, and you can go on for that like that forever. Though it's a lot still, but at least you can list it out in such a way that it corresponds with natural numbers. So it is countable despite Q being dense in R. So again, the cardinality is Aleph null. Cardinality is Aleph null. So the cardinality is still that special and Aleph null. Okay, because it is countably infinite. All right, so let's move on to real numbers now. So real numbers within whatever range is uncountable, like we've seen already, because no matter how hard you try, you can never get all the real numbers there are. So we have that. So of course, this is uncountable. It's uncountable. Okay, because Cantor's diagonal argument shows that R cannot be listed in a sequence. Cantor's diagonal argument. Cantor's diagonal argument shows that R cannot be listed in a sequence. So now the cardinality, of course, the cardinality is the continuum. So this special C I told you about the other time, small c special. So it's the continuum, which is greater than Aleph null, which is that special n, not. So that's that. So, I mean, understanding this concept is crucial in set theory and helps us to grasp different sizes of infinity, which is a fundamental idea in higher mathematics. So with this, we come to the end of this video on countable and uncountable sets, which has been a very interesting ride. All right. So if you have not subscribed to this channel, you want to do that right now. And of course, hit the notification bell so you can always get alerted when a new video is released. See you when we talk about applications of set theory in the next video. Bye.